if you're given a vector, we will often need a unit vector that points in the same direction as the given vector. This process is called normalizing the vector. So how do you do this procedure? Basically what you do is you take your given vector, and to get the unit vector, to normalize the vector, to get a vector in the same direction, what you end up doing is computing the magnitude of the vector you have, and you do 1 over that magnitude. Remember, magnitude is a scalar or a number. So 1 over should be a number. And you take that number and you scalar multiply by the vector. So for example, the vector v with components 3 and 4, we saw that the magnitude was 5. So then if we follow this procedure that's now I highlighted the key part in red, if we define a new vector called u, and we do 1 over the magnitude, so 1 over 5, times the vector 3 comma 4, now let's apply the scalar multiplication as defined for a scalar times a vector, and you get the vector with components 3/5, 4/5. And that was the vector that earlier was defined to be u. And if you just actually run that vector through the magnitude formula, you will see that the magnitude is 1. Okay, let's do a couple example things. If you have the point 2, -5 as A and the point -3, 11 as B, let's find the vector v that starts at A and ends at point B. So here I went through doing -3 minus 2 to get the -5 for the first component, and then 11 minus -5 to get positive 16 for the second component. Now, as a follow-up, let's take this vector that we just computed, -5 comma 16, and let's find 10v. And let's also find the magnitude of the original vector. And then let's find a unit vector in the same direction as v. So 10v is just, well, there's your scalar multiplication, right? So -50 comma 160. The magnitude of this vector v itself, just run it through this formula that was reminiscent of the Pythagorean theorem, and you get root 281. And the vector u, just according to that normalizing procedure, should be 1 over root 281 times the vector -516. And so when you do that scalar multiplication, you get a thing that looks like this. I am really not worried about radicals in the denominator in this class. Just leave it like that. I would like you to verify that this works for the interactive question. I know this sounds a little strange, but answering this in this way, I think, will help stave off the question that students really want to ask. The typical question people want to ask about normalizing a vector, which the process is shown here. I mean, it's done. But people want to say, how does that end up normalizing the vector at all? People don't want to multiply by 1 over the magnitude of the original vector. People just sometimes want to multiply by the magnitude itself, not the reciprocal of the magnitude. And it turns out that this is the thing that works. So I want you to verify that this is the thing that works. In other words, I want you to take this vector right here, and I want you to show me that that vector has length 1 using the magnitude formula. So not as in the form of belief or anything like that. Please take this vector. I mean, the task is take this vector, go back to the magnitude formula, and show me your algebra steps here. This is a place where I really don't want you to skip any algebra. I really just go through the steps. The algebra is a little tedious, but it's not that bad. If you go through this process once, I hope this really convinces you, by example anyway, that the procedure that occurred here was the correct procedure. You really should verify that this vector here has length 1. That then I think will really help. You know, it's just the thing that works, that creates the vector to be the desired length. Okay, here's a vector that we're going to need later. Just position vectors, remember, start at the origin. The position vector ends at there is one position vector which ends at the origin. So let me step back. Just make sure. Let me step. Okay, just step back again. Position vectors always start at the origin, and so there's a position vector corresponding to each point in the plane in 2D space. Like so, every 2D position vector corresponds to a point in the xy plane. In fact, if you appreciate this language, there's a one-to-one correspondence, or there's a bijection between position vectors in 2D space and all the points in the xy plane. Okay, but one position vector then ends at the origin as well. So this, what I'm talking about is, it's a position vector, so it starts at the origin. But this vector also ends at the origin. It starts and ends at the same place. It's a vector that doesn't go anywhere. It's the 0 vector, right? So because the vector ends at ordered pair 0, 0 in parentheses, then the components would be 0, 0. So that this vector, it's called the zero vector. Nothing fancy. It's just to notate the vector, it's a zero with an arrow above it. But to spell out what it really is, it's in angle brackets 0, comma 0. And same deal in 3D space. Context always clarifies which of these it is. So if you're doing a problem that's in 3D space, 0 with an arrow above it just means angle bracket 0, comma 0, comma 0, close angle bracket. By the way, note that the magnitude of the zero vector is the zero scalar. The zero vector, by the way, cannot be normalized. If you try to do that, you can give it a try. You end up dividing by 0 at some point. Just as a preview for something we'll look at for the next day's worth of slides is that the dot product of a vector with components a1, a2 and a vector with components b1, b2 is a scalar. And that scalar is multiply the first components of the two vectors and multiply the second components of the two vectors and take those products and add them together. That is going to be denoted with a dot. The dot is required in a dot product. You cannot skip writing the dot there. You will need to use this app to answer the next question. So please open this app on your own. What appears to happen geometrically with the vector a1, a2 as its components, and the vector b1 and b2 as its components when the dot product is close to 0. So take a look down here, at least for the default that as the screen loaded, the dot product of the two vectors, all the work is shown for you here. It ends up being -10. But I just want you to play around and see what seems to happen when this, sorry for how it jumps, but that's because the computation is a different length at different times. So now the dot product is a little bit bigger than 20, but try playing around with this app a little bit. Move the points around, which will change the two position vectors, and see if you can get the dot product to be 0 or very close to 0, and see just what seems to happen in that case in making that occur. Okay,